All right, so we've been saying that positive and negative charges attract. That's what's known as Coulombs Law, right? And it's just that opposites attract. There's an equation for it. So the energy of this attraction is equal to some constant, which is just these fancy numbers and symbols. We don't have to worry about that too much. And then times Q1, Q2 over R. This Q1 and Q2 are our charges of our ions. And the thing we want to note here is that the bigger these charges are, the more energy we're going to release. So the bigger the charge, the more attraction we're going to have. So for example, like a +2 -2 charge is going to be more energetically favorable than like a +1 -1. The other part of this is the R, the radius, or really the distance between our two charges. And if we think about this, it's in the denominator. So as this number gets smaller, our overall energy gets bigger. We release more energy. So what we say here is that when our ions are closer together, we have more attraction. And Coulomb's law is actually very similar to something maybe you're a little bit more familiar with, and that's the equation for gravity. So if we think about gravity, it's very similar. Here we have the masses of the object, whereas over here in Coulombs, we have the charges. So the more massive the objects are, the more they're going to attract one another, right? Earth has more gravity than you do. And then the distance, right? The further apart objects are, the less they'll attract one another, right? So we don't feel the gravity too much from some distant galaxy. Remember that we said that the greater the magnitude of the lattice energy, the more stable the ionic compound is, the stronger that ionic bond is. So we're going to compare different ionic compounds and state which one is has the stronger ionic bonds or is the more stable one. So let's compare lithium chloride versus cesium chloride. The first thing that we want to think about is the charges. In lithium chloride, we have a +1 -1 charge. And in cesium chloride, it's the same thing, +1 -1. So the charges are the same. So that's not what's going to determine which one of these is more stable. The other thing we want to think about is the radius or the size of our atoms and how far apart they are one another. If we think about where the periodic table is located, we have lithium somewhere down here and then cesium below here. So as we go down our periodic table, we get bigger. And so if we kind of draw like what an image would kind of look like, this lithium chloride would be something like this, whereas this cesium chloride would be something kind of like this. And we can see that this distance is smaller than this distance over here. So the cesium plus is bigger than our lithium plus, right? The other, the anion is chloride in both sides, so it's, same thing there. And so then what we say that charges closer together in the lithium chloride, right? The charges in the lithium chloride are closer together than the ones in the cesium chloride. And so what we say then is that lithium chloride has more lattice energy. Its magnitude of lattice energy is greater. It is going to be the more stable lattice. It's going to have the stronger ionic bond. And if you compare the lattice energies from the literature, for lithium chloride, it's going to be -834 kilojoules, whereas cesium chloride is -657 kilojoules per mole. Note that these are both negative numbers because we're releasing energy, we're becoming more stable. And so we can see that the magnitude of the lithium chloride value is larger than the cesium chloride, right? They're negative numbers, it's a little bit weird, but just think about kind of absolute value. So there's an example of size being the factor. The other factor, right, as we said, is charge. So we could compare something like sodium fluoride versus something like calcium oxide. In sodium fluoride, we have a +1 -1 charge. In calcium oxide, we have a +2 -2 charge. And so we think about one of these charges is bigger than the other, right? The calcium oxide has the bigger charge. And so then that's what's going to be the stronger ionic bond, right? We said according to Coulomb's law, the stronger your ionic bond, the more lattice energy you're going to release. And if we look at these values right here, for sodium fluoride, it's negative 910 kilojoules per mole. And then for calcium oxide, it's negative 3,414 kilojoules per mole. So you can see that the calcium oxide ionic bond is much stronger than the sodium fluoride. And then finally, what if you compared, both charge and size? Which one of these is a bigger factor? Well, if we look at our charges, while they are different, the numbers are still relatively close to one another. Whereas size, they're relatively close to one another. Whereas when we think about charge, these numbers are much more different than one another. And so if you have both factors changing, both size and charge is what's going to dominate, right? So we're going to say charge is the bigger factor. So charge is the most important thing. That's what you want to take a look at first. And then after you've sorted it by charge, then you can take a look at the size. Of course, take a look at the work along for some practice.